Hey folks, in today's video we're going to be taking a look at multiple linear regression. Now multiple regression is a lot like simple regression, only instead of using a single predictor variable to make a prediction about a dependent variable, you're actually using multiple predictor variables still to make one prediction about a single dependent variable. So in simple regression you've got one x and one y. In multiple regression you've got a number of x's, multiple x's, and still one y, one dependent variable. Most of the same concepts from simple linear regression apply to multiple regression. In fact, multiple regression is still creating a best fit line through the data, only in multiple regression the data is multidimensional. Ooh. So you're actually still using the least squares method, where you're finding the smallest sum of the squares of all residuals, meaning differences between the data points and the predicted line. But in multiple regression, it's more complicated. So let's take a look at what an equation for multiple regression might look like. This equation, I really should have put a little dot here, but this shows actually what a multiple regression equation would be with three predictor variables. So I've got an x1, an x2, and x3. And this you should recognize this. This looks similar to the equation you get for simple linear regression. But we've got three x's, three different types of x's, three predictor variables instead of just one. So this is our y-intercept. That's we've also got a coefficient for our x1 predictor variable, a coefficient for our x2 predictor variable, and a different coefficient for our x3 predictor variable. And then we've still got an error term, which is to say, there's always going to be some amount of uncertainty with our regression equation. It's never going to be entirely accurate. So this is the error term that's also present in simple linear regression. So what do each of these coefficients say? Well, obviously this is the y-intercept, but this b1 here says for a single unit change in x1, y is going to change by b1. It's the exact same interpretation you have with simple linear regression. Same thing over here. For a single unit change in x3, y is going to change by b3. This is just sort of, you can almost think of it as like three separate slopes. That's not maybe a good way to think about it, but what would be the slope in simple linear regression applies to every single predictor variable in multiple regression. So the possible objectives of multiple regression include, one would be just to come up with an entire predictive model for your dependent variable. You want to know how y is affected by all of these factors. Another very common reason you might run multiple regression is actually to determine the relationship between maybe one or two predictor variables and the y variable, but you throw in a whole lot of predictor variables to control for their effects. In other words, if what you're really interested in is one or two predictor variables, you got to factor in the effects of all these other predictor variables to get the true effect of the ones you're really interested in. So maybe we really want to know what the relationship is between x1 and y. But we threw x2 and x3 in there because we want to control for their effects and get a more accurate coefficient for x1 in predicting y. We'll look at an example to illustrate this. All right, so let's say we got a situation where we want to know the relationship between the size of a house and its eventual sale price. Maybe we're a real estate company and we want to be able to say, predict what a home is going to sell for according to its square footage. Why wouldn't we just run a simple linear regression where our predictor variable is square footage and our dependent variable is the eventual sale price of the house? Well, we could, and that would give us, some relationship, but we can get a more accurate understanding of the relationship if we factor in some additional variables in order to control for their effects. So we could add in additional factors, such as the median household income in the neighborhood that the home is selling for, the age of the home, the size of the lot, and the quality of the local schools, for instance. And that's going to, if we throw all of those into our multiple regression, it's going to give us a more accurate coefficient for the square footage and its effect on the home sale price. Let me use one of these I'll expand on the quality of the local schools and to sort of explain how the effect that this could have. Imagine that all of our data is coming from two neighborhoods. And one of those neighborhoods tends to have pretty small home sizes in terms of square footage, but that neighborhood has just the best local schools, and so a lot of people want to move there. If you don't factor in the quality of the local schools, your results in terms of the predictive power of square footage on home sale price might look a little bit strange, because you're going to see a lot of small houses selling for relatively more. But once you factor in the quality of the local schools, that predictor variable is accounted for, and your coefficient for square footage is going to change to reflect this. So what I mean by that is, when you run multiple regression, all of the different factors you're going to get a coefficient for each predictor variable that has taken into account all the other predictor variables you've added. So you could actually see, if you started off by running an equation that had 2 predictor variables, imagine that we don't have a third variable here. If you then rerun using the same data but add in another variable, so let's say we started out with square footage and medium neighborhood income. When you add in the age of the home, the coefficients for square footage and medium neighborhood income are both going to change. Then if you add in the size of the lot, the 3 other coefficients are also going to change. So they all take, each one of the coefficients is affected by all the other predictor variables you have in there. And as long as they're all good variables, you're going to get essentially more accurate results for the relationship between each and the dependent variable. So now, picking the right independent variables, the right predictor variables to run in your multiple regression is really, really important. This is pretty much a science in itself. But the bottom line is, you really want to pick predictor variables to run in your regression that make sense. Another way to say that same thing is, don't pick variables that are stupid. For instance, if you want to measure the efficiency of a manufacturing plant, don't use as a factor what color you paint the exterior of the plant. If you want to know how someone's going to vote, it doesn't really make sense to ask and run in your regression the last time it's been since they got their haircut. This is not just sort of common sense. It can actually really mess up your regression. Because sometimes dumb predictor variables that you run will actually come out as significant in your regression equation. Sometimes this is because there's another factor that influences both the predictor variable that you ran and the dependent variable. So I could see, for instance, if you ran when the last time someone got their haircut and how they're going to vote, that there might actually be a significant relationship, because there might be a relationship between factors that do make sense in terms of how someone's going to vote, say age, gender, racial or cultural background. Those might all affect both how someone's going to vote and how long it's been since they last got their haircut. So you want to be careful about throwing in stuff that doesn't make sense and then saying, well, it's significant. Also, I mean, if you run enough stupid factors, and you say, like, oh, I want to be 95% confident that each one of my predictor variables is significant based on the tests that we looked at in the previous video, 95%, 1 out of 20 is going to come out as significant even if it really isn't. So that's just type 1 error. So the bottom line is, don't pick stupid variables. Pick variables that make sense. Another thing, and this is a lot more subtle, that you want to consider is choosing variables that don't have redundancy in terms of their predictive power. This is a concept that's called multicollinearity. And what it means is, you might have 2 variables, both of which sort of make sense in terms of they might both have an effect on the dependent variable, but they might be having basically the exact same effect. And so what the trouble with that is that then it's hard to know which of them has more of the effect, or if either of them have a significant effect. It's going to look something like this. If this is our y, sort of everything we need to know about our dependent variable, everything we could know about our dependent variable, we might have one factor that tells us that much, and another factor that tells us that much. So we'll say this is This is the predictive power of x1, and this is going to be the predictive power of x2 over here. It's hard to separate them out. So generally, you want to try to avoid picking variables that are pretty much redundant. So here's an example. Let's say we wanted to know the factors that affect the teaching efficiency, the effectiveness of K-12 teachers. And so we throw in a variable, predictor variable for the highest degree that teacher has earned, but then we also throw in a variable that's the number of years of schooling that they've had. Obviously, those are going to have pretty much the same effect. They're almost the same thing, just stated in a different way. Not exactly, but you can bet that there's going to be a huge effect of multicollinearity. They're basically going to have a big overlapping effect. And you might, even though they might be, either one of them might be a significant factor, when you run your multiple regression, you might get a kind of large p-value for each of them. And essentially, you'll say, looking at those results, you might say neither one of them is a significant factor. And that's just because they're overlapping so much. A more subtle example we could go back to our housing prices example and say, well, what if we ran something for square footage? Remember, this is our key predictor variable. This is the one we really care about. But then we also throw in another factor for the number of bathrooms that a house has. Well, presumably the square footage and the number of bathrooms that a house has are going to they're going to be highly correlated with each other. And that's really what multicollinearity is when you have two x variables that are highly correlated with each other, and therefore their effect on the dependent variables is kind of going to be the same. So you want to watch out for that and try not to run variables that are going to have a high correlation with each other. The bottom line here is what you're really looking for is to come up with a good predictive model that's informative, but also practical. Basically, you can take a look at the results, see your coefficients for your x variables, and actually use that in a way that's actionable and where you can actually make use of those results. So that all comes into picking the right independent variables. Okay, so let's take a look at an actual multiple regression output. In our videos on simple linear regression, we use this example of a basketball team. We used a predictor variable of the team's shooting percentage in a game, and the dependent variable was their points scored. So we wanted to figure out a relationship between shooting percentage and points scored. We can continue to use this example, but I'm going to add in some additional factors. So let's show those here. What if we wanted to know also the effect of turnovers, the number of turnovers that a team has, its effect upon the number of points scored? And so presumably, we already looked at how the higher a shooting percentage, there was a positive coefficient for shooting percentage. Obviously makes sense. The better that a team shoots, the higher the number of points scored is going to be. We would expect a negative relationship with turnovers. So the higher number of turnovers a team has, the lower their point scored, because they're not getting as many shots. They're turning the ball over. And let's add in one additional factor, and that would be where they played the game. Generally, basketball teams tend to do a little bit better on their home court. They got their own fans there cheering for them, and a little bit worse away. So we might expect, when they're at their home court, they are going to score more points, and when they're away, they're going to score probably less points. And we've also got a neutral site here, so okay, something in between that. Let's use these in our multiple regression. But can we? Can we actually just use everything that's listed right here and run a multiple regression? Well, turnovers and shooting percentage, those work, but we can't use site. They don't have numerical values. So can we use it? Well, the answer is yes, but obviously not in its current form. We have to assign numerical values to this site, to this factor of site. And what are our possibilities there? Well, could we just say, neutral is 1 or 0? And so maybe say neutral is 1 and home is 2 and away is 3. Does that make sense? Well, no, I don't think so. I mean, first of all, it doesn't really make sense to assign maybe even rankings to these. Actually, if we were going to rank them, I'd maybe say like away was 1 and neutral is 2 and home is 3. It's not good to rank them, first of all, because it's making a big assumption. Now, maybe that assumption makes sense based on what we know about basketball, but it's not really good scientific practice to make an assumption and sort of... Apart from that, it really, what we're doing here is we're assigning weights to each of these sites. And that really, that's no good. These are not, it does not make sense. Is home 3 times as good as away? No. I mean, who knows? We can't really weight these. What it's going to be much more safe to do is to assign a separate variable for each of these possibilities. In other words, we're going to assign a variable for home. It's going to be binary. They are either home or they're not home. And so we'll assign it a value of 1 if the team played that game at home, and a value of 0 if they played it on a neutral or away site. This is just the variable for home. So we say home is either going to be 1 or 0. It's 1 if they're home, 0 if they're not home, whether they're neutral or away. And we'll add another variable for away, where it gets a 1 if they're away, and a 0 if they're neutral or home. Now, the trick here is we don't actually have to assign a variable for all 3 of these possibilities. We're only going to assign a variable for 2 of them. That doesn't really make a lot of sense, but let me explain it. It might not make intuitive sense, but let me explain it. We sort of need a default, something that everything else is compared to. So I might say, I'm going to create a variable for home, a binary variable for home, a binary variable for away, and then leave neutral alone. In other words, if both home and away are 0, that means it's going to be neutral. And the coefficients that I'm going to get for home and away are all going to be compared to as if they were at a neutral site. So I'll get maybe a positive coefficient for home. That's what I would expect. They play better at home than when they're at a neutral site. And presumably I'll get a negative coefficient for away, which means they're going to score less points away at a visitor when they're the visitors than when they're at a neutral site. That's my hypothesis. That's my prediction. But we have to have something that we're comparing the other dummy variables to. So the default is going to be neutral, and the coefficients we get for home and away are going to be as compared to a neutral site. So we need that baseline. Now, that's totally arbitrary. I could have said home is going to be the default, and we're just going to assign a binary variable for away and for neutral, and I would expect the coefficients on both of those to be negative, because they'll be negative as compared to when they play at home, where we would expect they would score the most points at home, so we'd expect the coefficients for neutral and away to be negative if home is our default, the one that we don't assign a variable to. This process of making non-numerical values into their own separate binary variables, assigning a 1 or a 0, these are called dummy variables. And so this is how it might look based on what I was saying before. If I make neutral the default that we're going to compare home and away to, you can see every time there's a neutral site, home and away, both these 2 new variables, these 2 dummy variables I just created, are going to be 0. If the team is home, home gets a 1, and away gets a 0. If the team is away, away gets a 1, home's going to get a 0. You're never going to see home and away both with a 1, because that would imply that they were playing both home and away, which is not possible for one game. So this is how we create the dummy variables. And now we have all numerical values. We are ready to run this multiple regression. Thank you for bearing with me. We're actually going to revisit dummy variables in a little bit more detail in a later video. So if that didn't make perfect sense, well, hopefully it will in round 2. All right, so let's go ahead and run this regression. Now, again, there's many ways you can run regression, including many ways in Excel, but I use the data analysis add-on. So I go to data, click on data analysis. I do not want a random number generation, I want regression. Click OK. My Y input range is points scored, that's my dependent variable. And my X input range is going to be all of this. I don't have to select each column separately, I can just grab them all. I have labels here, meaning I check the box for labels, meaning my top row is, these are labels, non-numerical values. I need to recognize that. I'm going to put a 95% confidence interval. And let's run this thing. All right, let me zoom in for you. This is my multiple regression output. I'm going to delete a row here just so we can see everything. Actually, you know what? Well, okay, that's fine. I don't even need this. All right, so what do we got here? Well, a lot of this should look really similar, or it should by and large be very similar to what you've seen with simple linear regression, especially our summary output. I mean, very similar things listed here. First of all, we have the number of observations. Up here we have the multiple R. The multiple R is the coefficient of multiple correlation. It's kind of like the correlation you get in simple linear regression where you're comparing one X and one Y. You say, what's the correlation between these two variables? When you're doing correlation between two variables, the value is going to be between -1 and 1, depending on whether it's a positive correlation, meaning they both, when one goes up, the other one tends to go up as well, or if it's a negative correlation, meaning when one goes up, the other one tends to go down, and vice versa. In multiple regression, it's all the multiple R is always going to be between 0 and 1 because it's sort of more complex, and so it's never going to be just straight positive or negative relationship between all of your predictor variables and your dependent variable. What the multiple R does tell you, though, between 0 and 1, it tells you sort of the strength of the relationship between all of your predictor variables and your single dependent variable. Now, saying strength of the relationship, a statistician would probably, I'm sure, would disagree with me, but it's sort of a simple way to think about it. The R squared, this is the same concept as with simple linear regression. The R squared, if you'll recall, is the amount of the proportion, since we're dealing with decimals, the proportion of the variance of the dependent variable, the proportion of the variance of the Y variable that is explained by all of the predictor variables you've included in this multiple regression. So that was the same thing with simple linear regression. You said the proportion of the variance of the dependent variable that is explained by your one X value. In this case, it's all of your X values. So again, it's sort of like the strength of the predictive model. You can say, well, you know, if R squared is high, you're saying we're really predicting a lot about the variance of the Y variable using our X values. And this really is kind of context dependent in terms of how to interpret the strength of that predictive power. But, you know, that's the simplified version. And that's, I think, what we want here. Now, adjusted R squared is something new. This is adjusted R squared is actually probably a better measure of the strength of the predictive power of your regression model, because it factors in the number of predictor variables that you've included. Remember I said, because here's what happens with the R squared. R squared always goes up when you include new predictor variables. And I said that one of the really important things with multiple regression is to choose predictor variables that make sense. Not to choose stupid independent variables, not to choose stupid predictor variables. You don't want to throw just anything in there because it might come out as significant, but it'll always increase R squared. R squared never goes down. It always goes up whenever you add in new predictor variables, no matter how inane those predictor variables may be, and no matter how insignificant and non-useful. I need some better language to describe what I'm trying to say, but they might be in actually determining a predictive relationship between all your variables and your dependent variable. Adjusted R squared, it actually factors in the number of predictor variables you've chosen to include. So even though R squared is always going to go up, no matter how stupid the variable you threw in there, adjusted R squared will probably go down if that variable really isn't adding much to the relationship. Because adjusted R squared is adjusted for the number of variables you've chosen to include. So what you're really kind of trying to do in terms of picking variables to include in your multiple regression is get the highest adjusted R squared. Because that's going to say, like I said, R squared is always going to go up. So you can always just keep throwing junk in there and R squared will go up. But adjusted R squared might go down if you've chosen to include, when you add in another predictor variable that really doesn't add much to your equation. So striving for a high adjusted R-squared. And adjusted R-squared is a really good, like I said, it's kind of a good factor to gauge the success you've had in choosing predictor variables, because multiple regression is often a very iterative process. You might start off with some predictor variables and say, well, these aren't significant, or I need, I wonder if I add some additional predictor variables. So you might take some out. If they're not significant, you might throw some more in that you think might improve the predictive power for your model. So you're striving for a higher adjusted R-squared with each of these iterations. All right, now let's take a look down at the actual X variables, the predictor variables, and look at their coefficients and their significance. Let's start, okay, we have our coefficients. These are, according to this model, if you increase the turnovers by 1, say, we would expect the number of points scored by the team to go down by about 0.96. How do we interpret the coefficients for a dummy variable? Well, this says if we're at home, we would actually expect to score 0.937 additional points as compared to a neutral site. Interestingly, this is not what I would have expected. If you're away, you would actually score even more, an entire over a point more as compared to a neutral site. In shooting percentage, as your shooting percentage goes up by 1, you would expect to score 2.53 points additionally. So that's coefficients and how you interpret them. But now let's go ahead and look at the significance of each of these factors. Because remember, that's what we want to, we want to make sure that these actually have a significant relationship at, say, 95% confidence. And that, the way we do that is exactly the same as with simple linear regression. We could look at the p-values, first of all. And so starting down here, shooting percentage still is extremely significant. Remember, if we said we want to be 95% sure that a factor is significant in terms of its predictive power with regards to the dependent variable, the p-value should be less than 0.05. And so this is clearly less than 0.05, so this is significant, as is turnovers. But when we get up to the dummy variables that we included, home and away, well, those don't look so significant. So, we can't say that these actually have any effect upon the dependent variable based on these p-values. The other way to think about significance is basically you want to make sure that you want to be, say 95% confident that the actual relationship is not 0, that the real coefficient is not 0. And so when you take your 95% confidence range, 0 should be nowhere within that range. So it's not here, but it's almost, smack dab in the middle of the range for home and away. So what do we do with this information? Well, what I would do is, like I said, multiple regression is an iterative process. You would probably want to take out these variables. You might choose to substitute in another variable, like number of days of rest for the team, something to that effect. But I'm going to go ahead and just run this regression again after taking out these variables and seeing what happens. So let's do this regression again. Get the same Y range, but now I want a different X range. I'm just going to include turnovers and shooting percentage. And let's run this thing again. I don't need these. So now we've run the regression. This is still a multiple regression because we've still got more than one X variable. We've still got 2 predictive variables, turnovers and shooting percentage. Still got our Y-intercept, our constant. And let's see. We would expect our now, it didn't look like home and away had much of an effect at all, and we would actually expect there not to be much multicollinearity between home and away and turnovers and shooting percentage, but maybe. We would still expect our coefficients to change slightly. So let's just look at this one. Turnovers was, in our new model, is negative 0.98. Over here, when we had home and away factored in, it's negative 0.96. So not much of a change, but you can see coefficients change, as do p-values. So the p-value we would expect to have seen change a little bit as well. Yeah, it certainly has changed. So this is just to reinforce the point that all of the factors you choose will affect all of the others. And let's take a look up here. Now, when we had all four factors, we had all four variables, we had an r squared of 0.98, sorry, that's 0.892. And we would expect that to go down once we remove those other factors, because r squared always goes up when you add in additional factors. So yeah, now it's just 0.89. So we lost about 0.002. But we would actually expect our adjusted r squared to go up. So we started out with an adjusted r squared of 0.863 when we had all four factors. And now it is 0.877. So it has actually increased the adjusted r squared by removing those factors. So we sort of have we would say maybe a better predictive model after we've dropped those two variables. So like I said, it's an iterative process. We might now go back and add in some additional variables and see what kind of results we get. See how our adjusted r squared is affected. All right, so just to wrap this thing up, let's go ahead and make a prediction for our points scored using our new multiple regression equation. Keeping in mind, so we've dropped the dummy variables home and away. We no longer care about the site because we weren't able to determine that it was a significant relationship with points scored. So now we've just got our two independent variables for our multiple regression. Let's say we have turnovers, 15 turnovers in the game. And a shooting percentage of 49%. And we'll make a prediction on how many points are scored in the game. So we say it's going to be equal to the intercept plus turnovers, the coefficient for turnovers times the number of turnovers, plus the coefficient for shooting times our shooting percentage, which was E4. And we would expect, if we have 15 turnovers and shoot 49%, to score about 107, this team would score about 107 points in that game.